recall that these slides are where? You can find these slides in Blackboard. Thank you. Okay. In the section with the course, movies, and notes. So these are replacing what would have been the notes if we were just writing things out. Okay. Let's go back one and see if we can figure out what's going on here. Recall the other day we ended with a problem, well, it's not written here, with fence up against the barn and trying to figure out how big of an area to make to keep the goats in. Okay? Here's something a little bit different. You have probably all at some point or another encountered a cardboard box where there's a tab of tape that wraps around each of the four corners of the box to keep it held together. Often things like the little PAWS, P-A-A-S, Easter eggs are in a little box like that, and other things where it doesn't take a particularly strong box to hold it together. When you go to make a box like that, the way the box is made is by starting out with a big chunk of cardboard. And then from each corner you cut out a little section. And when you cut out the little section from each of the four corners, you're left with a piece of cardboard that looks like what's in the lower left of the slide. To make the box, you just fold up the four tabs and then stick them together, usually by just running a little piece of tape around the corner. Okay? No big surprise there? Well, the idea here is you're going to make a box by cutting out 2-inch squares from each side, and you're told that the box is to be 6 inches longer than it is wide. Okay, so whatever the width is, and the width would be this. Do I know what the width is going to be? Got no idea, do I? All I know is that the length is going to be 6 inches longer than what the width was. So that means this length here is going to be the width. Well, I didn't know what that was. But it's going to be that plus another 6 inches. Does that make sense what just happened? Okay. So one of the tricky things is realizing how this looks with the corners cut out. Another is, how do you write the length and the width using just one variable? Sometimes people are tempted to call this the width and this the length, and you're up a creek because now you got two variables. That makes it a lot more difficult to solve. If you write it with just one variable, it's a lot easier. Okay, let's see. If the box is to have a volume of 224 cubic inches, okay, so the volume is going to be 224 cubic inches. What are the dimensions of the piece of cardboard? Notice it doesn't ask what are the dimensions of the final box. They're asking what size cardboard do we need to start out with. So you know what the thing needs to look like in the end, and the question is, well gosh, how big of a piece of stock material do we need to start with? Does that make sense what's going on here? Okay. They actually do stuff kind of like this in box industry. And actually there's a good living to be made designing boxes or cans. Really? Yeah, I've got a friend that went into that, cutting paper and stuff. Okay. 25 years ago, he was making about what I make now. Okay. So let's think about this a little bit and see if we can figure out what's going on. Well, we know that this dimension here is our width. That's going to be x. We know that this dimension here is our length. That's going to be x plus 6. Hey, what's the height of the thing going to be? What's the height of the box going to be? 2. Yeah, because that's going to be the result of that little tab, isn't it? That's where it folds up, so the sides are going to be 2 inches tall. Okay. Well, what we can do from there is we've got our box. Okay, I'm setting this up a little different than what they did. And we can take this x plus 6 times the x times the 2. Now those are the dimensions of the finished box, aren't they? And what that's going to need to figure out too is 224 cubic inches. Is everybody okay so far? I can divide both sides by 2, and at the same time I'll multiply by the x. I'll get x squared plus 6x equals 112. Does that make sense what I did there? I did 2 steps at once, which is going to give us then x squared plus 6x minus 112 equals 0. Myron, can you use that magical new quadratic formula on your calculator? Okay, yeah, so let's help Myron. What value goes in for A? Did you find it okay?
Yeah, I got it.
Okay, so it's A question mark. So what number is going to go in for A? 1. What number is going to go in for B? 6. And then what value will go in for C? Negative 112, and the negative's down at the bottom, not the subtraction sign. So you put in a negative 112, enter.
And I got solutions, which is 8 and negative 14.
X equals 8 inches. Good. X equals a negative 14 inches. Now, you got to be kind of careful here. Okay? What do we have to be careful of? They're both good answers. Does one of the answers make sense as far as building a box? You can't build a box that's a negative 14 inches long, can you? Even though mathematically this works, in the construction world, in engineering, that's not going to work, which tells you that x has to have a value of 8. So that means this side's going to be 8 inches long. This side's going to be how long? 14 inches long, and the other's going to be 2. Well, okay. Well, that's all well and good, but that's the dimensions of the box. We don't want the dimensions of the box. We want the dimensions of the piece of cardboard, don't we? Well, let's go back over to the diagram on the left. The width of it is supposed to be 8 inches based on what we just solved for. The length of it is going to be this 14 inches. Now you got to be careful here. Is the length and width of the cardboard when we start going to be 8 by 14? No. Why not? What's going on? Yeah, we've cut 2 inches off on each end, haven't we? So be careful, this isn't going to be 10 inches. This is not going to be 10 inches because you've cut off 2 inches here and here. So what's that really going to work out to be? 12 inches. And the same thing holds for this. By the time you're done backing things up before you cut off, you've got to add another 4 inches there, and this is going to wind up being 18 inches. Does that make sense? Pretty easy, isn't it? Yeah, when you do it, Chuck. Okay. Now, when we go to the next screen here, look at this one. They set things up a little bit differently. They called the cardboard's length x and x plus 6, didn't they? Not the box, which means then that this length right here is going to be the x subtract the 4 inches from the 2 tabs. This length right here is going to be the x plus 6 subtract the 4 inches, and I'll give you the x plus 2. Is that wrong to set it up like that? No, all you have to do is keep track of what x actually represents. There are two ways to set it up. Either will work. And if you take a look down here, look what they get for their answers. They get x equals 12 or x equals negative 10. And if you take a look, the x equals 12 is the width of the cardboard, isn't it? Which means the length of the cardboard is going to be 12 plus 6 or 18 inches. And either way, you get the same dimensions. Well, which way should we do it? Whichever makes sense to you. Either will work, okay? And they'll both give you reasonable solutions. Okay. All right, that's got that squared away. Discard the inking. Get rid of that one, and here we go. Okay. So what we did in the last one was took a look at how can you use quadratic formula to solve some problems. Okay. We're headed into complex numbers at this point because when you do some of these quadratic formula problems, you're going to wind up with complex numbers. You're going to wind up with numbers like x equals 3 minus 0.5i. And that's a completely legit number. Nothing wrong with that number. But what does it mean? Well, that's what we're going to take a look at here is what's a complex number. Okay. We're going to take a look at how do you work the basic add, subtract, multiply, divide on them. Then we're going to look at some quadratic equations that give them. Okay. Some things to keep in mind. There are really 4 of them. They list 2 of them here. The other 2 I would like to see is I cubed equals negative I, and then I to the 4th equals 1. These 4 are some basic facts you need to be familiar with. The square root of negative 1, up to this point you've always been told you can't do the square root of a negative, right? You can. But it moves you into a different set of numbers. Imaginary numbers. It's kind of like, oh gosh, we were going to go out and play football, but there was an ice storm. Now there's 3 inches of ice out there. We can still go out and have fun, but now instead of football, we're going to play hockey or something like that on the ice. Okay? We're just changing the game. New rules with a new game, right? Hockey and football don't play by the same rules. I don't think you're allowed to use sticks in football. Okay? So what's going to happen is the rules are going to change, but we can still go out and play a game. Different game, but can still go out. With I equal to the square root of negative 1, it allows us to compute a solution for x squared plus 1 equals 0. Up to this point, you've always been told, yeah, that just isn't going to work. It actually does work. The solution is going to be x squared equals negative 1. X equals the square root of negative 1, right? Which is I. Okay, complex numbers come in what is called standard form. The standard form, you've seen me write a couple of them. It has a real part and an imaginary part. So if we have something like 6 plus 4i, this first section right here would be the real part. Real because it's a real number that's being used there. The second portion of it's going to be the imaginary part. And I suspect you can imagine why that's called the imaginary part. Right? Because it has an imaginary number associated with it. There it is. It's also possible on these numbers, which are in the form a plus bi, to have a couple things happen. First off, if a equals 0, then what you're going to get is just 0 plus b times I, which is just b times I. This would be some examples like 7I, negative 3I, 2/3 I. And these are what are called pure imaginary numbers. Pure imaginary because the only thing that's there is the imaginary part. Okay? What if b equals 0? Now what do you get? Well, you get a plus 0 times I, which is just going to be a. Some examples of that are things like 2, 9, negative 3/4. Hey, have you seen numbers like that before? Those are what kind of numbers? Those are the real numbers, aren't they? Yeah. So if the b is 0, you're back to the real numbers, where you're used to working. Okay. So you can wind up with all kinds of mixes and matches here. If a is greater than 0, okay, suppose we have something like this, square root of negative 3. This is the same thing. This can be written as square root of negative 1 times 3. Does everybody buy that? Now, this doesn't work for adding, but if you're multiplying, you can separate it into two separate square roots. If you're multiplying, not if you're adding. And that lead square root is just going to be I times the square root of 3. Does that make sense to everybody? If you have something like, let's say the square root of negative 7, that's going to be the square root of negative 1 times the square root of 7, which is going to be I times the square root of 7. Is that working? Okay. Wow. Now, you got to be a little bit careful on these. For example, in the case of this first one here, I wish I could cover up the bottom part. This would be I times the square root of 3 times I times the square root of 3, which is going to give you I squared times the square root of 9. Everybody okay so far? What's I squared equal to? It's going to be a negative 1 times, and the square root of 9 is 3. So this is going to give you the negative 3. In the case of the second one, you're going to have I times square root of 2 times I times the square root of 8, which is going to give you I squared times the square root of 16, which is going to be a negative 1 times 4. Which will give you a negative 4. Is that working? What if you have something like this? Let's say negative square root of, let's say 12 times square root of negative 3. What's that work out to give you? If you had the square root of negative 12 times the square root of negative 3, what's that going to work out to be? Negative 6, yeah. Okay, in the first case, it's going to be the square root of a negative 1 times the square root of 12 times the square root of negative 1 times the square root of 3, which is going to be I squared square root of 36. The I squared's a negative, and what's the square root of 36? 6. Does that make sense? Okay. You can add and subtract these puppies too. The way that you add these is just like you would probably guess. In the case of this first one here, all we're going to do is we're going to combine the real parts. Negative 3 plus a positive 5 is 2. Then we're going to have 4i minus I is going to give us 3i. Okay, aha, there it is down there. B. This is going to be a negative 7i. Now I'm going to distribute that negative. So it's going to be minus 6 plus 5i. Does that make sense what I did? Okay. What we're going to get is a negative 6. You always list the real part first. Then you have a minus 7 plus 5 is minus 2i. You good so far? How do you think you would do part C? About FOIL. Because when you square it, that means to multiply it times itself like that. When you FOIL this out, you're going to get the negative 3 times the negative 3, which is going to give you 9. That's that times that. Next thing you're going to do is the outer 2, and you're going to get minus 6i. You'll do the inside 2. Let's see. Yeah, it's going to be a plus 2i times a minus 3, and that's going to be another minus 6i, isn't it? Plus 4i squared. Is everybody with me so far? This then's going to work out to be 9 minus how many I? Okay, you have minus 6i and minus 6i. So you have minus 6 and a minus 6 gives you minus 12. Now, this one you got to be careful of because it's 4 times I squared. But what's I squared equal to? Negative 1. So it's going to be a minus 12. Is that completely simplified? No, not yet. You're absolutely right. You've got the 9 minus 12, which is going to be a minus 3 minus 12i. Does that make sense on foiling that out? The last one, the 17 divided by 4 plus I. Now that one gets a little bit interesting. Huh. Minus 12i. Okay, I may have made a mistake here somewhere along the line. Yeah, where'd I get 12? It's going to be a minus 4. There, let's try that. Which will give us then the 5. Thank you. Be nice if I could add, huh? on the last one, and this is the tricky part. Adding, subtracting, multiplying are not horrible. Dividing isn't horrible either. It's a little different than what you might expect. If you have something like 17 divided by 4 plus I. Think back to the old days where you had things like 3 over the square root of 2. Okay? The maneuver was to get rid of the square root in the denominator, wasn't it? And the way you did that was you multiplied by a square root of 2 over a square root of 2, which would give you 3 square root of 2 over 2. Does that look familiar? You do kind of the same thing when you get a fraction with a complex number in the denominator. What you do is you multiply by, and don't let this scare you, you multiply by the complex conjugate. That means it's a complex number with the opposite sign. Opposite sign on the imaginary part. Now, what you've done here, or what's been accomplished here, is this kind of sets it up like, remember if you, back in the good old days, take something like x plus 3 times x minus 3, it gives you x squared minus 9. It gives you a difference of squares, doesn't it? So by multiplying by the complex conjugate, it set it up to be a difference of squares, just like up at the top of the screen. And what this is going to give us then is we're going to have the 17 times each of these, which will give you 68 minus 17I over, we got to do this FOIL stuff down at the bottom, don't we? You're going to have the 4 plus I times the 4 minus I. That's going to give you 16 minus 4I plus 4I minus I squared. Now, because you've got the plus and the minus going on here, the two inside terms are always going to subtract out. And that's going to give you 16 minus a negative 1. What's 16 minus a negative 1? 17. So the cool thing is the denominator now has a real value for that part of the fraction. All that has happened really is we've taken the complex part and we've moved it up to the top, haven't we? Okay. So with division, it's not so much division as it is just getting a denominator that's a real number. That's about the best you can do on that. So is the adding, subtracting, multiplying, dividing make sense, look reasonable? Well, yeah, in cases like that. So for example, let's say you had 12 over 5 minus 2I. How would you go after that one? If you had 12 over 5 minus 2I. Yeah, that one's going to leave a mark, isn't it? We're going to multiply by 5. Is it going to be minus or plus? Plus 2I. And you're going to do that both in the numerator and in the denominator. And what that's going to give you then is we're going to have 60 plus 24I. There's the numerator. Now comes the messy part. We've got to multiply the denominators. Well, the first two is going to give us a 25. The outside 2 is going to give us plus 10I. The inside 2 is going to give us a minus 10I. And then for the last part, we're going to get minus 4I squared. Does that make sense to everybody? So the inside parts are going to cancel out. And what we're going to have is 25 what? Plus 4. because the I squared's a negative, so we're going to have a negative 4 times a negative 1 gives you a plus 4. And that's going to give us then a denominator of 29. Did you survive, Farmer?
Yeah.
Good. You're welcome. I hope you have a good weekend. Does that make sense on how to redo these fractions? I almost hate to say it's dividing because it isn't. It's just rewriting it with a real number in the denominator. Okay, so now you've got a little bit of an idea of how to go about working with them. How do you do quadratic equations? Because sometimes they're going to have these complex solutions as well. Okay? If the discriminant is negative, you know you're in for a complex number, aren't you? Because you're going to have something like a negative b plus or minus. Now, if the inside part's negative, you're going to have something like negative 17 over 2 times a. Now, let's say that's a 4. Let's just call this negative b a 6. Do you see if that's going to work out to be a complex number? Anytime the discriminant is negative, you get a complex number. Now, really important, if you have a quadratic with a complex value or solution, all that means is the graph never touches the x-axis. It's either always above the x-axis or below it, one or the other, but it never touches. There are no real solutions, but there are complex solutions. Well, that's kind of weird. Okay, try these. Uh-oh. Now, you can either wince in pain at this, or do like Myron's doing. What are you doing? Yeah, he's going to pull up the quadratic formula. How long do these take to solve on the quadratic formula? About as fast as you can type them in. And after you get done with one and it gives the answers back, all you do is press enter and it'll bring back up a equals, and you can go right on to the second one. And press enter and then go right on to the third one. Now you do have to be careful in the second and third, because are those okay to plug in the way they are? No, the second one needs to be rewritten a little bit. I would rewrite this as 0.5x squared minus 5x plus 17 equals 0. And remember, you can't use the quadratic formula if it's not equal to 0, right? So you've always got to get it equal to 0. In this second case, you're going to get a minus 2x squared minus 3 equals 0. Did you do okay?
Yeah. That's
Super. Okay. I'll see you on Monday.
Yeah. I'm trying to do the first one. Okay, I'm getting it early.
On which one?
The first one, I plugged in 1 for A, 3 for B, and 5 for C, and got it early.
That's weird.
Yeah.
Try B and see what it does. So you put in the 0.5. Yeah, see what happens on part B. Negative 5 and C is 17. Okay, so yours is, for whatever reason, not doing the complex numbers. I don't know. It's time to go visit the math lab again.
You just have to go to mode and go down where it says like real and switch over to A plus B.
Oh, okay, so thank you. Yeah, because it won't display it under, yeah. Okay. Whew.
If you do the basic one, do you guys switch it back?
No. it's
Nope,
not.
it'll be okay.
Thanks.
Okay, yeah, real important. On your calculator, okay, here's the screen. Here's that first row of keys, and then you get into the actual keys. Right up in this area, I think it's the second button. Right there it says mode. Under mode, you go in and you may have real highlighted, move it over so complex is highlighted and press enter. So that'll roll your calculator over to now do computations in the complex numbers. Thank you. I appreciate that. All right. Now, what if you don't have this on your calculator? Well, that's okay. I mean, you don't have to. You can go about the process of, let's see, we could solve this one. We're going to get a negative of a negative 5 plus or minus the square root of b squared, so that's going to be 25, minus 4 times a half times 17, all over 2 times a, that's 1. And you can work that out by hand each time. That looks like fun. Okay, so you can do it whichever way you want to. Doesn't make a whole lot of difference to me. Okay, oh look, works each of them out here. So on part A, plugged in the numbers just like we said, and what you're going to get inside the square root is you're going to get a square root of 9 minus 20, which is going to be square root of negative 11, which is going to be equal to I times the square root of 11. Oh, there it is. And then you can report your answers like that. Everybody good? When you go to graph something like this, it doesn't intersect the x-axis, so that's kind of a problem. How would you graph that? Well, a couple ways come to mind to me. First, you could go to, on your calculator, if you have a graphing calculator, you could put in y1 equals x squared plus 3x plus 5 and let it graph. And when it graphs, you'll get something like there. Or the other thing that you can do, if you don't have a graphing calculator, is you can do x squared plus 3x plus something or other plus 5 minus that same something or other. Uh-oh, what am I setting up to do here? Complete the square. Oh no. So this is going to be 3 over 2 squared. So we're going to add 9/4. And to compensate for adding 9/4, we're going to subtract 9/4. So this is going to factor into x plus 3 over 2 squared plus 5 is really 20 over 4 minus 9 over 4 is 11 over 4. Hey, does this give you where the vertex is? Yeah, the vertex sorry, it's kind of hard for me to write on the bottom of this, is going to be a negative 3 over 2, 11 over 4. And if you take a look at that, is that about where it looks like the vertex is on this? Negative 3 over 2 is 1 1/2. Well, 1 1/2 is about there. 11 over 4 is right around 3. Well, that's right around there. A little bit less than that. And you can see that the vertex does wind up in the same place. It's opening up because the lead coefficient is positive, and it's going to be a normal width because the coefficient is 1. So there you go. And this allows you to then identify the exact location of the vertex. Everybody good with that? Okay. There's that one. Another way to look at this too, on this second one, is you want to know where the 1/2 x squared plus 17 is the same as 5x. Well, 5x is a graph of a line. The 1/2 x squared plus 17 is the graph of a parabola. And another way to look at this is, where does the parabola intersect the line? Well, based on that graph, where do they intersect? They don't. So the solutions to this wind up being imaginary. If you were to graph this on your calculator, you couldn't get answers to this, could you? There are no answers in the real numbers. On the third one, that's pretty straightforward to solve. You can just take and divide by the negative 2, and you get x squared is equal to this negative 3 over 2. Then when you take the square root, you get x is equal to plus or minus the square root of negative 3 over 2, which is going to be plus or minus. The negative comes out as an I, square root 3 over 2. Everybody good? Okay. Same deal with this last one. You've got these two functions. You're asked, where does a negative 2x squared equal 3? Well, negative 2x squared never does get up to 3, as you can see in this graph. So where do they intersect? They don't. This would be one that you could not solve with a graph. Oh man. So maybe getting that quadratic formula is a good idea. Let's see, we're a couple minutes short, aren't we? Maybe getting the quadratic formula is a good idea.